Hello, dear students. I welcome you all to this lecture series on theory of semigroups with course code MMDE 405. In this second lecture, we discuss semigroups and then we give certain examples of semigroups. So let's first define binary operation. As you all know that we recall that definition of binary operation. Binary operation. So let S be a non-empty set. Let S be non-empty set. A function O from this Cartesian product S cross S, cross product, you can see cross product of S with itself, S cross S to S is called a binary operation. Binary operation. So any such function with domain S cross S and codomain S is called a binary operation on S. It's called a binary operation on S. Here we use the multiplicative notation for this binary operation. So note throughout this lecture series we use the multiplicative notation for binary operation. Throughout this lecture series we use multiplicative notation for this binary operation, that is the image of any ordered pair with entries in S. Image of S1 comma S2 is denoted by S1 S2. It's just a multiplicative notation. Or in other words, you can say here this AOB. Sorry, it's S1O S2 is equal to S1 S2 is equal to S1 S2. Next, we define groupoid. If O is a binary operation on if O is a binary operation on S, then this ordered pair SO. If O is a binary operation on the set S, where S is a non-empty set, then the ordered pair SO is called a groupoid. So groupoid means suppose अगर हमारे पास कोई non-empty set होगा, इस पर कोई binary operation O होगी, then this order pair S together with this binary operation O, it's called a groupoid. So next we define a semigroup. So a groupoid is said to be a semigroup if the binary operation is associative. A groupoid S with binary operation O is called a semigroup. If the binary operation O is associative, that is S1O, S2O, S3 is same as S1O, S2O, S3, and in the multiplication notation we have S1, S2, S3, it's equal to S1, S2, S3. That's this. This is true for each element, S1, S2, S3, and for all elements, these elements they belong to S. तो ग्रुपॉइड को हम उसी टाइम कहेंगे कि ये सेमी ग्रुप है if the binary operation O, which is on that S, if that binary operation is associative. Associative means if it satisfies this property. So there are a number of examples of semigroups. Suppose we have set of natural numbers with multiplication. So examples are this set of natural numbers with multiplication, set of natural numbers with addition. These are the examples, or you can say this interval 0, 1 with respect to multiplication, usual multiplication. They are all examples of examples of semigroups. These are the examples of semigroups. Now we define commutative semigroup. What do we mean by commutative semigroup? Commutative, or you can say abelian semigroup or commutative semigroup. A semigroup S is said to be commutative. A semigroup S, it means there is a binary operation that is multiplicative. A semigroup S is said to be a commutative semigroup. A commutative semigroup. If xy is equal to yx for all xy belongs to S. तो commutative कब इसको कहेंगे? When it satisfies this property. If every element of S commutes with every element of S, that means at that time we can say that semigroup is a commutative semigroup. So next is the definition of a semigroup with unity or identity. If S is a semigroup, if S is a semigroup, contains an element 1, that's denoted by 1, contains an element 1 such that if S is a semigroup and suppose it contains an element 1 such that 1 into x is same as x, which is same as x into 1 for all x in x, for all x in S, for all x in S. A semigroup, if S a semigroup contains an element 1 such that this is true, this equation holds, then one is called the identity, then one is called identity of S, and the semigroup S with identity and the semigroup S with identity 1 is called monoid. Is called monoid. Is called a monoid. तो अगर हमारे पास सेमी ग्रुप होगा ऐसा जिसके पास ये एलिमेंट होगा 1, जिसकी ये प्रॉपर्टी होगी, अगर हम इसको किसी भी एलिमेंट के साथ मल्टीपल करें उस एलिमेंट पर इस 1 से कोई असर नहीं पड़ेगा. इट विल रिमेन द सेम. 1 into x is equal to x which same as x into y. तो ऐसे एलिमेंट को कहेंगे हम ये आइडेंटिटी है इस सेमी ग्रुप S की. तो अगर सेमी ग्रुप ऐसा होगा जिसके पास ये आइडेंटिटी होगी उन सेमी ग्रुप्स को हम कहते हैं मोनाइड. Those semi groups are called monoids. So monoid is a semi group with identity. तो अभी हमने कुछ एग्जांपल्स ली थी. Let's see this. N with usual multiplication, the interval 0, 1 with usual multiplication, they're all monoids. Here 1 is the identity, here 1 is also the identity because it's a semigroup with respect to multiplication. Here the operation is multiplication. Or monoids are monoids. But N with addition is not a monoid because it does not have an identity under addition. Is not a monoid. It's not a monoid. Even you can say this set of even natural numbers with multiplication is also not a monoid. Is also not a monoid. It's a semigroup but not a monoid. It's not a monoid. So these are the examples of monoids and these are the examples of semigroups which are not monoids. So one more example is every group is a monoid. Every group is a monoid. Every group is a monoid. This is trivial because a group is a semigroup with identity and each element possesses inverse. So that means every group is a monoid. So now we prove the following theorem. We showed as in case of groups, the identity of the group is always unique, and the same is true for semigroup. If it's a semigroup with identity, then identity of that semigroup must be unique. It has only one identity. तो जैसे ग्रुप्स में है ना आइडेंटिटीज आर यूनिक, वैसे सेमीग्रुप्स में भी ये रिजल्ट है. द आइडेंटिटी ऑफ द सेमीग्रुप इज यूनिक इफ इट हैज आइडेंटिटी. So let's prove this theorem. Identity of a semigroup is unique, or you can say identity of a monoid because monoid has identity. Identity of a monoid is unique. Identity of a monoid is unique. So proof is very simple. You assume suppose it has two identities. Suppose the monoid has two identities. So let S be a monoid. Let S be a monoid, and 1, 1 dash be two identities. Be two identities. Be two identities of S. We need to show that 1 is equal to 1 dash. So we show that 1 is same as 1 dash. Identity is unique. So we have now you can write this since 1 is the identity, so it means that 1 into x is equal to x is equal to x into 1 for all x in S. and 1 dash is also the identity, so it means that 1 dash into x is equal to x is equal to x into 1 dash for all x in S. So by definition of identity, so since this one is true for each x in S and 1 dash is also an element of S, therefore this is true for 1 dash also. This gives 1 into 1 dash is equal to 1 dash, it's equal to 1 dash into 1. And second is true for each x in S. In particular, it's true for x is equal to 1. And this one, 1 dash into 1 is equal to 1. It's equal to 1 into 1 dash. So let's compare these two. So this gives 1 is equal to 1 dash. So let's compare these two. This gives, because it's 1 dash is equal to 1 into 1 dash. Here it's 1, which same it's equal to 1 into 1 dash. So it means that 1 is equal to 1 dash. So because 1 dash and 1 as this, it is actually the image of, under binary operation, it is the image of 1 dash comma 1. It goes to 1 dash here under the binary operation, and here the same element, it goes to 1. And since that operation is the binary operator, that's a map from the cross product to this to the set S, and these two elements of the cross product, they are same as 1 dash 1 dash 1 1, they are equal elements, therefore the image must be equal. And here the image is 1 dash and here it's 1, so that means this 1 is equal to 1 dash. So therefore identity is unique. Therefore identity is unique. Therefore identity is unique. Now suppose the semigroup, given semigroup does not have identity, but we can adjoin an identity to this semigroup by introducing an extra element which we denote by 1. So suppose, so that's the end of the proof. Now suppose the semigroup S does not have identity. Or it's without identity. Suppose the semigroup S is without identity, is without identity. Suppose S is a semigroup and it does not have identity, it's without identity. Then we adjoin an extra element 1 to S. Then we adjoin an extra element 1 to S. We adjoin extra. It's without identity, without 1, but we can adjoin this element 1 to S, 1 to S to form a monite, so that it will become a monite by defining. We define because we have to define the multiplication of the elements of S with 1, as one was not initially present in this semigroup. So by defining this x into 1 is equal to 1 into x is equal to x for all x in S. And now we define its product with itself. 1 into 1 is equal to 1. So now you can easily verify that this S union, that's element 1, is a monite. Is a monite. Then S union 1 is a monite. It's a monite and is denoted by and is denoted by S1. S1. So what's S1? S1 means that if the S semigroup S is without identity, then we can adjoin 1 to S. So in that case, S1 will be S union 1. And in case the semigroup has already identity 1, then S1 is same as S. So now we define this. It's denoted by this. It's like this S1 and it's denoted by S1, where this S1 is defined by and is defined by and is defined by and is defined by S1 is equal to, it's equal to S union 1 if S is without identity. If S is it's equal to S, it's equal to S if S already, it's equal to S if S already if S has already identity, and it's equal to S union 1 otherwise. तो हमने क्या डिफाइन किया, हमने पहले सबग्रुप को डिफाइन किया, फिर आइडेंटिटी को हमने डिफाइन किया, उसके बाद हमने ये कहा कि अगर इसमें आइडेंटिटी नहीं होगी हम एक एक्स्ट्रा एलिमेंट इसके साथ जोड़ देंगे। तो वो एक्स्ट्रा एलिमेंट हमें ऐसा जोड़ना है सो दैट एक्स्ट्रा एलिमेंट विल बिकम एन आइडेंटिटी। तो वो हमने ऐसे जोड़ लिया 1 to S with this operation x into 1 is equal to 1 into x is equal to x, 1 into 1 is equal to 1। अब ये जो नया सब ग्रुप है S जिसके साथ हमने 1 को जोड़ लिया, इसको हम S1 से डिनोट करते हैं।